Hello everyone, let's talk about exponential growth and decay. So we're going to start talking about logarithms, but if you're going to do logs, you need to know how exponential functions work. So first thing we're going to talk about is compounding interest. So the formula that you may have seen in the past is you have your principal, that's the amount you're going to start with, and then you have to calculate your growth or decay factor, which I will start with 100%. I'll do this slightly differently. 100% plus whatever your interest rate is, and we're going to talk about doing this with different times per year, different ways to compound interest in a year. And then depending on how many times you compound the interest, that will be your exponent. I think it's easiest to see a couple of these problems for this to make sense. So this says $1,000 is invested at an interest rate of 12% a year. That's a crazy good interest rate. Find the amounts after 3 years. So our principal is $1,000, so that will be 1,000 times. My growth factor is 100% plus 12%. And since I'm doing it annually, I'm just going to say it's 12%. That's this n is 1. If you do it one time per year, then it's 1. So that's 112% is my growth factor, which is a decimal, is 1.12. Remember, you move the decimal twice or divide by 100. That's what percent means, out of 100. So my growth factor is this whole thing, 1.12. 1.12, and we'll say to the power of how many times we're doing this? 3. So this is where you will definitely need a calculator, and I'm going to start to kind of streamline this here in a second. We're going to do 1,000. I'm going to type it in a special way, though. 1 plus 0.12 divided by 1. Since we're doing it annually, it's per 1 year. And then to the power of 3 years, and we're doing it once per year. So it's annually, so you're doing it for 3 years, and you're doing it once per year. So it's a total of 3 times your compounding interest. So 1404.93. 1404.93. That's if you compound your interest 1 time per year. Now we're going to talk about doing it semi-annually. So semi-annually means twice a year. So to do the same thing twice a year, I take that same equation that I have and I just have to tweak it a little bit. So let me show you how that looks. If I take this same equation and I change it to be twice a year now, you have to take the interest rate and cut it in half, and then you have to say, well, we're not just doing it once a year, we're doing it twice a year. So you take half the interest rate, but you do it twice as often. And you might think, well, won't you get a lot more money? No, you'll get a little bit more money, though. $1,418.52. 1418.52. So notice, by simply compounding the interest differently, I made 14 bucks more. Cool. Quarterly. Quarterly means 4 times. So I will do the same thing, but I will do it 4 times. So I'll take this equation and I'll say, all right, quarterly means you take the interest rate, you divide it by 4, but instead of doing it once every year, you do it 4 times every year. So there's 1425.76. So we went from 1418 to 1425. We made another 7 bucks by compounding the interest a little bit more often. Monthly. Okay. Monthly. All right, let's do divided by 12. There's 12 months in a year. So I'll say, okay. Second, insert 12. All right, and now I have to do 3. For 3 years, 12 times a year. 1430.77. Now you might be noticing that this thing's starting to level off a little bit. The first jump, we went up about 14 bucks. Then we went up about 7 bucks. Now we only went up about 5 bucks. When we go to daily, you're going to see we have diminishing returns in compounding interest. It's not going to always keep getting better and better and better for us. So we'll start to say, okay, there are 365 days in a year. 365. Oops, I need to insert that parentheses. And I'm going to do for 3 years, every day, 365. Whoa, it didn't work. 365. 1433.24. So notice how going from 12 times in a year up to 365 times in a year only gave me an extra 3 bucks, 2.5 bucks. So it's not going to change a whole lot when I go to hourly. But let's try and figure out how many hours there are in a year. If I take that, well, you know what? I'll just take the days and I'll just say, well, let's multiply by 24. So I'm going to try and use parentheses here. If I do this carefully, I think it's fine. So I want to insert parentheses, 365, and I'm going to say There's 365 days in a year, and there's 24 hours in a day. So if I put parentheses there, it'll calculate that for me, and then I can also do it up here, 365 times 24. And that gets me 1,433.33. 1433. So notice, going up to hourly only added, what, 9 cents? So you can see, if I do by seconds, I probably won't change it at all. And there's some asymptotes going on here we could talk about when we get to E. But right now, I just want you guys to notice that compounding interest different times per year will give you different values. It's the same process every time. You just have to know, like, how often are we going to do it. There's a video that goes with the Futurama problem, so you can watch the video. If you click the link, you get the watch the whole thing. But this says he's got 93 cents in his bank account, and that's the year 2000. So we'll say 0.93, and my interest rate, I'll take 100%, and I'll add 2.25, which is 102.25, which is a decimal, is 1.0225. Okay, that's percent. This is decimal. So my starting amount is 0.93. My growth factor is 1.0225, and it says we're doing it annually, so once a year for 1,000 years. So you start with less than $1, and then if you fall asleep for 1,000 years, how much money are you going to have? 0.93 times 1.0225 to the power of 1,000. Holy cow. That's okay. 1,000. 4.3 billion. It's pretty good, right? This is 3 million. That's 4.3 billion. Okay, let's do the same thing, but we will calculate it now semi-annually. So I have to use the formula a little fancier now. 1 plus 0.0225. So cut the interest rate in half. If it's semi-annually, that means you're doing it twice a year. And then it will now be for 2,000 years. 1,000 times 2 is 2,000 years. So you get about the same thing. You get, well, I mean, you get $0.6 billion more. That's not a bad deal. So 4.3 billion, 4.8 billion, pretty cool. 4.3 billion. And then this one's 4.8 billion. That's a lot of cash from going from $1. Watch the episode. He spends it on a can of sardines. Or no, anchovies. It's the last can of anchovies. I think they're extinct. All right, now let's talk about how they actually calculate interest. If you're going to calculate interest as a bank, you're not going to say, hey, we're going to calculate all your interest on one day. Just from a honesty standpoint and accuracy standpoint, if I knew that the bank was going to compound interest on January 5th, I would take all the money that I could come up with, put it into that account, get the interest on it, and then go do that with every other bank that I could. So you can't calculate interest in one day. They do it, we call it continuously. So we use a slightly different formula, and it comes from this number E. Essentially what happens is if you take this idea that we've seen in the other equation, 1 plus 1 over n to the nth, that's this guy right here. As you get more and more intervals of time, it stops becoming important, like we started to see, like the difference between days and seconds was not very much, or days and hours was not very much. Because if you graph this, it gets closer and closer to this value of E. E is about, I think it's like 2.71. You have it on your calculator down here, right there. That's that E. Wait, no, actually I want to use, that'll do it, yeah. 2.718, okay. There's E, or you can use this button as well, E to the power of, which is what we'll normally do. So this is one of those irrational numbers that comes up a lot in finance problems. Let's use it. We take the same idea, you take the principal, how much you start with, but then instead of calculating an interest rate, you just say E to the power of whatever the rate is for however many years. So if this is continuous, we would say you start with $1,000, E to the interest rate is 0.12, and it's for 3 years. So it's very similar to what we did before, but it's a slightly different formula, and we're going to get a slightly different answer. Where'd my calculator go? Come on. Come on, calculator. There it is. Okay. Let's get this out of here. So back to my calculator, I'm going to say very similar to what we did before, 1,000 E to the power of 0.12. So the interest rate's 0.12, and we're going to do that for 3 years. So we get 1433.33. 1433. Now this is the same numbers as the other one we did, so let's go back and look at example 1. 1433 is what we got when we did it hourly. Well, it turns out doing it more than hourly doesn't make any difference. You're doing it continuously. You're essentially imagining that the chunks of time are getting smaller and smaller and smaller until they are 0. The limit would be 0. So you can notice how it's like calculating interest the best on our end, but it's the most accurate for the bank. Let's do another continuous problem. So one thing that you see a lot of are these like radioactive decay problems, and this is saying it's decaying at this rate. So first says, what's the mass at time 0? If I plug in 0 there, you might realize that then it will be e to the 0 power, so that's just going to be 1. It will come out to be 13 because the exponent's going to go away. You can use your calculator, but you can see that if you have an exponent to the 0 power, it's going to go away. If I do 13, up here, 13 e to the negative 0.015 times 0, you get 13. It's your starting amount. After 45 days, you take the same thing, but you just say, well, it's not 0 days, it's 45 days. And after 45 days, there are 6.619 kilograms. 6.619 kilograms. So this is called radioactive decay. And it's saying that you started with 13 kilograms, and now we're down to 6.619 after 45 days. That's a very common type of application for E. So the main thing is that you guys understand how to start with an initial value and then compound interest, or in this case, radioactive decay. So that's it for exponential growth and decay. Be sure to hit that like and subscribe button.